So let's do a precipitation reaction problem. We're going to predict the products, balance the equation, and give the net ionic equation for the reaction. So if this were a test, a quiz, or some type of assessment, we'd first want to know what kind of problem it is and what do we need, what knowledge that we have gained do we need to apply. Well, this tells us that it's a precipitation reaction. So that's fairly obvious in that case. Other times we might look for the word complete the precipitation problem, or when I mixed these two things together, a solid formed, and that would hint that it's a precipitation problem as well, because that's really what they are. Precipitates are insoluble, so they do not dissolve in the solvent anymore, which is usually water. So a solid of some form is created from things that were previously able to dissolve in water. Usually that means that a new product was created. So that gives us a little bit of hint on then what to do. So we have our magnesium chloride, which is aqueous. Remember, when we see an ionic compound, and I can tell it's ionic because it's a metal with a nonmetal, when we see an ionic compound with this AQ next to it, that really needs to tell us in our brain that these two aren't really together. Right? They're actually dissociated. I always think of it like a dance party. They're out and about in the dance party. Plus silver nitrate, a good time to practice our naming. Silver nitrate, again, dissolved in water, so aqueous. That means it's dissolved in the water. And then we should get two products from this. At least one of which might be now in the solid form, which we would call the precipitate. So in order to do this, one thing to remember, and different people like to approach these different, is precipitation reactions are double displacement reactions, or wife swapping, or switching of dance partners, whatever kind of helps you with that. So then when I go to create my two products, the first thing I want to do is switch the dance partner. So let me show you some different strategies for thinking about that. You can put your outside partner, point of living if I can't do it in green. So our outside partners, my magnesium and my nitrate, I could put them together, and then put your inside partners together. Right? So that's one strategy of thinking of it, outside partners and inside partners. What you don't want to do is put your magnesium with your silver. And the reason for that is, by convention, when we write ionic bonds or ionic compounds, we write the cation first and then the anion. Cation and then the anion. These are not reflecting their actual charges, just whether they're positive or negative right now. We'll come back to their actual charges in a second. And so magnesium and silver are not going to be able to make an ionic compound because we need a positive with a negative. We need ones that will be attracted to each other. So that's why we have to make sure we get our outside, our positive with our new negative, and our positive with our new negative. So then when we go to do that, so let's put magnesium with nitrate. It doesn't matter if I had chosen to do the other one first. There's no convention there. You should list your positive one first. That's just convention. Magnesium with nitrate. Nitrate is a polyatomic ion. It does not come apart in a precipitation reaction. So just take your whole polyatomic ion and move it over here. And then plus, so there we have silver. We list our positive one first. And then our chloride. Now I am not going to bring this 2 over, because just because it needed 2 chlorides over in this ionic compound, that does not mean that it's the same ratio here in my product. So I did need to bring the 3 over because that's the chemical formula for nitrate. But chlorine, this is chloride ion, doesn't have a particular chemical formula. So that can be a little bit confusing. So take your whole polyatomic ion, right? That's subscript 2 because it's really just this one big particle. Think of it like that. Right? With a negative charge. And then over here, this chlorine is just reflecting the ratio between the magnesium and the chloride. There's 2 chlorines for every 1 magnesium. So step 1, let's create steps as we go. So step 1, switch your dance partners. Create your 2 new compounds, right? Now, step 2, check their formulas. Let's go ahead and write that, and then I'll explain what I mean. So just because we switched them does not mean that this is actually the correct formula for magnesium nitrate or silver chloride. And this is where we need to consider then those charges and what they really are. So let's talk about those. So magnesium, if I locate it on the periodic table, I can see that magnesium would have a +2 charge because it's an alkaline earth metal. Whereas chlorine has a -1 because it's a halogen. If you're not sure how I'm getting that, we might want to refer to some earlier videos or send me a message. So that right there explains why we needed those 2 chlorines, because we needed 2 of those to balance out every 1 magnesium. But over here in this, so chlorine has this -1 charge, right? I'm going to put that up here so that I remember it. We don't actually include the charges in the chemical formulas. That's why I usually try to do it above to kind of show my thinking, but it's not part of the formula. Now, what about silver? Silver is one of those funny ones that you kind of have to just know, or you can do some deducing. I know that the charge of a nitrate ion is -1, and I just know that from studying my polyatomic ion flashcards. And since it's a 1-to-1 ratio, you need 1 nitrate for every 1 silver. That tells me that silver is a +1. I also use a technique on the periodic table starting with aluminum, which is a +3, and I kind of go diagonal 3, 2, 1 to get to silver. If you want to know more about that, send me a message. So that tells me +1, -1. Oh, this is the correct formula. So I've checked one of their formulas and it's correctly. Now you might be thinking, what about this 2? Well, we'll deal with that when we balance it. We'll deal with that later. Right now we're just focusing on, is this the correct formula for the product? So what about this one? Well, you can tell over here, we're kind of already pointing out to our problem. This is a -1. This is a +2. These do not add up to 0, and that's what we need. We need them to cancel out. So I need 2 of the -1s, right? It's -1, -1, that's -2, and that would add up to 0. So in order to do that, I need to put parentheses around my polyatomic ion. And that is because when I put the 2 there, I want it to not look like 32. The only time I need parentheses is when I have a polyatomic ion. So notice I don't need them around the chlorine. And I need more than 1 of that polyatomic ion. Notice I don't have parentheses over here when I only had 1 nitrate. So I have checked my formulas. Ta-da! Okay, next step. Determine the solubility. What am I going to put? Determine their state. I guess maybe that's the better way to say it. Determine state of your products. So I need to figure out what I mean there is, what am I putting here? So let's go back. What am I putting here in this little parentheses? Like for state, my options really are, it's a gas, it's a liquid, it's a solid, or it's dissolved in water. Those are my options, right? I've probably said this before, but since we're talking a lot about solubility, it's really important to remember that that is not what the S stands for. The S does not stand for soluble in water. It stands for solid. I think that's a common bit of confusion. So how do I do that? How do I determine? I cannot just automatically assume they're still aqueous. This is when I need to bring in a solubility rules chart. You're not expected to memorize the solubility rules. You will notice you start to kind of pick up on certain ones. So I have this little tiny version of my solubility rules chart, and I'm going to start here with my magnesium nitrate. Now I notice nitrate right here in my soluble anions. So anions, just a negative particle. Soluble anion with no exceptions. Soluble anion, no exceptions. What does that mean? That means magnesium nitrate is soluble in water. Now I do not put an S there, because remember S doesn't mean soluble. I put an AQ. Dissolved in water. So if you find that it is soluble from your solubility rules page, then you're going to put an AQ to say that it is dissolved in water. They're not actually really attached to each other. What about silver chloride? Let me bring up my chart again that I had moved out of the way. So when I find let's find chlorine right here. There's chlorine. And it says, it says usually soluble. So when you say something like that, let's double check our exceptions. So soluble with some exceptions. So that means that if I have the exception, it's insoluble, which is the same way of saying not soluble. So notice this exception right here. This is one of the exceptions, which is the very thing I'm working with. So silver chloride rather than being soluble like chlorine ions usually are, is insoluble. So, oops, don't need that. That means silver chloride is going to get the S. Again, that doesn't stand for soluble, it stands for solid. And this, if I was asked what's my precipitate, silver chloride is my answer. This here is just actually going to be still dissolved in the solution. I'm not even going to be able to see it. It's going to be mixed in with the water. So this is going to be the precipitate that maybe I see. Oftentimes it'll just look like cloudy, and given time it might settle to the bottom. Now, the last step, and it's really important that you do this step after you do step 2. You cannot do step 4 before you do step 2, is balance. If you try to balance your chemical equation before you've made sure that the formulas are actually correct, you're often going to get something pretty crazy. So let's do a little bit of erasing so that you can, oh, I forgot, I'm going to erase my words too. Just a little bit, just clear up some things here. We'll get a fun bright color to, what color should we choose, y'all? Artie's green. Okay, so I like to start with my polyatomic ions, especially when they stay together like this, as they do for precipitation reactions. So we have NO3 and I have 2 of them. So I'm going to go ahead and put a 2 in front of that. So I have 2 of my silver nitrates to then get 2 nitrates and 2 nitrates. And then you notice that imbalanced my silver. So I'm going to come over here and I'm going to put a 2. Coefficient in front to balance that. And that actually fixed the chlorine problem that we were discussing earlier. We had 2 chlorides and we only had 1 over here. Well, now we have that fixed. And that's why don't bring the 2 over. You're going to account for it later. Maybe the 2 does need to come, but don't assume. Just move the chemical formula. But of course, this is the chemical formula for polyatomic ions. So this is what we would call the complete, right here, the complete molecular equation. And it's called that because they kind of look like molecules. Even though we don't use the word molecule for ionic compounds, they look as if they're molecules, and this is our precipitate. So it also asked me to write the net ionic equation. So the net ionic equation is when you get rid of the spectators. And you know, these are really our spectators. These ones that don't precipitate out, they're our spectators. So we're going to get rid of them. But we're also, it says net ionic. So that means we're going to be really showing these as ions dissociated in the solution. This is my personal strategy for writing a net ionic equation for a reaction. Rather than write the complete and then canceling out all of your spectators, I just think of it as the net ionic equation is telling the story of the precipitate. And so I bring the precipitate down and I say, okay, we made 2 AgCl, and that's our precipitate, and I know it's the precipitate because it's the one with the S. How did I make 2 AgL? I probably could get rid of the 2 because it's going to end up being kind of reducible in the end, but I went ahead and just brought it straight down, and you'll kind of see why. How did I make this, ignoring things like that brought, you know, the wingman that brought the ions to the party? Well, I made it by getting 2 silver ions. So when we're showing them as ions dissociated in water, we do need to include the charge. And here's my AQ to show that it was dissolved in water. There's a big difference between this and this. And I reacted it with 2 chloride ions. Again, I have the charge to show that it was dissolved in water. Okay. This might seem like kind of silly, like the charge, but if you think about a chemical formula, we can have, you know, solid chlorine or solid silver, which is not the same as silver ions. And so when we put a metal with a nonmetal, the fact that it's actually an ion as opposed to the pure element is implied. So if we put it all by itself, though, we don't have any way to know that it's the ion and not the pure element, and so that's why the charge is so important. So you'll notice the net ionic equation should show your dissociated elements, these are the dissociated ones as ions with their charge. And then we have dissolved in water, and solid. Practice makes permanent. Do as many precipitation practice problems as you can.